This video is sponsored by KiwiCo.
The James Webb Space Telescope is the instrument, right, that every single astronomer is excited for. We're on tenterhooks. We've been planning what observations we're going to make with it for years, decades even for some people, because it is set to revolutionize nearly every single field of astrophysics. But you might be thinking, well, Becky, why are you all so excited about this project? Especially because all that really hits the news about the telescope is the fact that it's overspent and that it's been delayed over and over and over again, meaning that, well, the public, like yourself, just don't have that same level of excitement as us astronomers. So I figured it was my civic duty, if you will, to make a video about why you should believe the hype. So the James Webb Space Telescope, or Webb, you'll sometimes just hear it referred to, or JWST as the cool astronomers like to call it, is a joint venture between NASA, the CSA, the Canadian Space Agency, and ESA, the European Space Agency. And later on in the video, I'm going to be chatting to Dr. Kendrew, who's from ESA, who's been working on the James Webb Space Telescope for 10 years, and she's going to give us the inside scoop. Now, it's set for launch on the 31st of October 2021, and we have all got all of our fingers and toes crossed that that actually goes ahead, because as astronomers have lived through many a disappointment with that launch date being put back. It is looking more and more likely. The final checks and tests are all being done as we speak, as I make this video in May 2021, before it's actually going to get shipped to the launch site of French Guiana, where it'll be launched on one of ESA's Ariane 5 rockets. Now, Webb is often described as a successor to the now 31-year-old Hubble Space Telescope, but as you can probably tell by just looking at it, it's very different to Hubble. First of all, the telescope itself is bigger. It has a 6.5 meter mirror compared to Hubble's 2.4 meter mirror. That's really important because a telescope's mirror is what it uses to collect light from whatever you're trying to observe. It takes that light and then focuses it down to a detector. So the bigger the mirror you have, the more light it can collect, and so therefore you can see fainter things which tend to be further away. The Webb telescope can only detect infrared light though, unlike the Hubble telescope, which could detect mostly visible light, but a little bit of ultraviolet and a little bit of infrared, sort of on the fringes of the optical wavelength range of light. Because it observes in the infrared though, and because it's so sensitive, it needs to be kept away from any objects that might be radiating a lot of infrared, which would cause noise in all of your images. Say, for example, like a planet of nearly 8 billion people, or I don't know, the sun. So unlike the Hubble Space Telescope, which is orbiting the Earth at a height of about 540 kilometers, Webb is going to be sent 1.5 million kilometers further away from Earth and further away from the sun to orbit the sun out there. It's something we call a Lagrange point. It's areas within the sort of Earth-Sun gravitational system that if you plonked something there, it would always stay at the exact same distance from the Earth and from the sun as Earth orbits the sun. So essentially, it ends up following Earth in its orbit, and spacecraft use them to essentially hover in those points. For example, SOHO, which is ESA and NASA's Solar Observatory, and then also the Discover satellite, which is NASA's Earth Observatory, they're both at L1, which is sort of the Lagrange point in the opposite direction. It's 150 million kilometers closer to the sun. It's just obviously the Solar Observatory is facing one way, pointing at the sun all the time, and the Discover satellite is always pointing the other way towards the sunlit side of the Earth. You've also got ESA's Gaia probe at L2 right now as well, which is measuring the positions and distances and motions of over 1 billion stars in the Milky Way. So this is something we've done before, and it's not new to Webb. But even at L2, 150 million kilometers further away from the sun than Earth is, you've still got a hell of a lot of radiation coming at you from the sun. So the Webb telescope will also have a sun shield larger than a tennis court, and it's made from 5 layers, each as thin as a human hair, and it's coated in aluminium and silicon, designed to reflect the sun's heat back into space. But we don't have a tennis court-sized rocket to launch the Webb Space Telescope on, so this sun shield, along with the mirror itself, have to be folded away to fit inside an Ariane 5 rocket, and then they have to be deployed once it arrives at this Lagrange point L2. One of the reasons for the delays to JWST was actually due to this sun shield. So they were doing sort of a test of this fold out of the sun shield back in March 2018, and it ripped. That can't happen in space after its launch. That would be complete mission over. You would not be able to use it as an infrared telescope because all you would detect is infrared radiation from the sun, and anything else would get lost in that background radiation. Same if the mirror didn't fold out properly as well, that would obviously be game over too. So it's really important that we constantly test all of these things to make sure they're going to work as we want them to out 150 million kilometers away from us, because if anything goes wrong, we can't fix it. Like astronauts had to do with the Hubble Space Telescope back when it had a mirror fault straight after its launch back in 1990. So once it's up there and, everything is hopefully folded out okay, which should take about 2 to 3 weeks or so, it'll then be time to check all of the detectors and the science instruments that are on board. The things that are actually going to record the light that the big mirror collects that can then send that data back down to Earth. Now, it's got 4 main instruments on board. One of them is called NIRCam, and that's been designed to take images at the optical end of the infrared wavelength range, and that's been led by a team at the University of Arizona. Then you've got NIRSpec, which is like a companion to NIRCam. It's working in the same wavelength range, but instead of images, it takes a spectra, which is where you take the light and split it into its component wavelengths, and you sort of get a trace of how much light of every wavelength you have. Now, you can do that for multiple objects at a time, or it can actually split up a single object like a jigsaw, which is great for studying galaxies and what's going on in them. That's been developed by ESA in Noordwijk in the Netherlands. Then you've got MIRI. This can take both images and spectra in one, with all the features of NIRCam and NIRSpec, but at longer wavelengths, right into the infrared. And this has been developed jointly by NASA and ESA with teams at the University of Arizona and at the UK Astronomy Technology Centre in Edinburgh, Scotland. And last but not least, we've got NIRISS. Again, it can take both images and spectra in one at the optical end of the infrared this time. This is the Canadian Space Agency's baby, and it's been developed at the Hertzberg Institute in British Columbia, Canada. Oh, and of course that all sounds great, but what does it mean in terms of what JWST will be able to actually see? Like, what science are we going to be able to do with this? Everyone talks about how it's going to revolutionize, every field in astrophysics. We can't go through every single field, but I've just picked 3 areas to highlight that I'm really excited about. The first is exoplanet atmospheres. So when an exoplanet passes in front of its star, some of that starlight will pass through the exoplanet's atmosphere. And on its way, it will get absorbed by molecules in the atmosphere, say something like carbon dioxide. And that'll leave a trace on the light that you can see when you split it into its component wavelengths through one of these spectrographs that's on the Webb telescope. You see these little dips in the trace of light where that light is missing because it's been absorbed by one of these molecules. The signatures of those molecules, though, are really faint. Combine that with the fact that the molecules that we'd be interested in actually detecting, things like water, carbon dioxide, methane, all the molecules that would maybe give away that life was present on that planet, they all absorb in the infrared. So this is why the James Webb Space Telescope is so perfect for this science, because it looks in the infrared, it can split the light with the spectrograph that it's got on board as well, and it's also got a giant mirror to collect as much light as possible with a hope of detecting these really faint signatures. So this is why exoplanet scientists are particularly excited, because they're all hoping that the Webb telescope will be able to detect Earth 2.0. The second thing I want to highlight is that the Webb telescope should help reveal how stars and star systems of planets are formed. Now, to form a star, you need hydrogen, but specifically, you need molecular hydrogen. That's 2 atoms of hydrogen that have bonded together to make H2. Problem, of course, is that the majority of hydrogen in the universe isn't in H2, it is just single atoms just knocking around. To make molecular hydrogen, you either need a lot of hydrogen in one place, which is sort of what gravity is responsible for, or you can also use dust as a catalyst to speed up that chemical process of bonding those 2 hydrogen atoms together. And when I say dust, I just mean like heavier elements and molecules that are just clumped together to make essentially like a grain, right? A grain of dust is maybe like a fraction of a millimeter across. So most stars that are forming today are forming in very dusty environments where these dust grains block visible light so that we can't see anything. But longer wavelength light, like infrared, doesn't get blocked by dust. We can still see the heat being given off by the stars. When I was doing a bit of reading for this video, I came across this analogy that I absolutely loved on the NASA website. It was just this man wearing a bin bag on his arm, demonstrating how we can still detect infrared radiation through the bin bag. I just love that. You go and work at NASA. What's your job today? Just stand there with a bin bag on your arm, please. So the Webb telescope, again, is going to be perfect for this. It's been designed to detect infrared light, so it should be able to see stars actually forming through these dust shrouds. And it'll also be able to help us test our ideas of how dust actually works as a catalyst to form molecular hydrogen. But also, we can see the stars forming, we can see the planetary systems forming around them as well. Because we think that all this dust eventually clumps together more and can start to form lumps of rock. So if we can see these planet systems being born, we can actually test our theories of how the solar system formed as well, and how these lumps of rock eventually clumped together to give us asteroids and planets as well. Again, I don't know how you can't get excited about the fact that JWST should be able to just, peer through this dust and watch protoplanets being born. And the third reason is that the Webb telescope should be able to see the first stars in the universe. So because light has a set speed limit, it takes time to reach us. So as we look out into the universe and see fainter things at greater distances, we're actually seeing them as they were when the light left them billions of years ago. And this is how we can understand how the universe has evolved, because we can literally watch it change as we look further and further back in time, because light's taken time to get to us. What it means is that the furthest things that we should be able to see are the first stars and galaxies that formed right after the Big Bang. Trouble is, those are incredibly faint. And the other problem is that the universe is also expanding, which means that the light that they give off also gets redshifted. Its wavelength is stretched out by expanding space on its way to us. So all that optical light that was given off by these first stars in the universe gets redshifted so much that by the time it reaches us, it's no longer optical light, but infrared light. That means that the Hubble Space Telescope can't even see these things. It can't detect the light from them anymore. So there's a limit to how far back in time Hubble can actually see. And this is why everyone's excited for the James Webb Space Telescope. It's been designed for this, right? It's got this huge mirror to collect as much light from these very faint objects right in the early universe that we have never been able to see before. Because what we really want to know is, how do those first stars and galaxies differ or are the same compared to the stars and galaxies we see in our own universe today? And what can that tell us about how the entire universe has evolved? These are the huge expectations and hopes that are riding on the James Webb Space Telescope's shoulders. So there is just 3 of the many, many reasons to be excited for the James Webb Space Telescope and all the science it will enable us to do. I wanted to get the inside scoop for you all, though, from someone who's actually working on the development team for the James Webb Space Telescope. So I called up my friend and colleague, Dr. Kendrew, who works for ESA at the Space Telescope Science Institute in Baltimore in the USA.
So I work for the European Space Agency, and I'm based at the Space Telescope Science Institute in Baltimore. We have a team of European scientists and engineers there who kind of, represent the European involvement in the mission. Specifically, I work on one of the 4 science instruments on board JWST. I work on an instrument called MIRI, which stands for the Mid-Infrared Instrument on the telescope. And I've been involved in this instrument for over 10 years now, since about 2008. I'm responsible specifically for one of the spectroscopy modes, the low resolution spectroscopy mode on MIRI. And so my job from day to day is incredibly varied. So some of it is, software and figuring out how we best operate and calibrate the data that we get back from the instrument, but also providing user support. So writing documentation, providing answers to people who want to use MIRI, and help them understand what the capabilities are and how they can best put together their observations, basically.
Nice. And I guess since you've worked so closely with MIRI and developing it and getting all of those help things online, by the time it's actually up and running, I guess you're hoping to use it as well for your own science. Like, what are you hoping that you'll be able to do with MIRI that maybe, or with JWST in general, that you haven't been able to do before, like questions that you haven't been able to answer before without MIRI?
Things I'm particularly excited about is looking at very dusty galaxies in the high redshift universe. And because these galaxies have so much dust in them, they're forming tons and tons of stars. But because of all the dust in there, we've not really been able to get much information about the stars because the starlight is kind of hidden behind these curtains of dust. And so we've really needed an observatory like JWST to really kind of probe deep into those kind of dusty regions and see the stars, get the light from the stars that's behind them. So that's something very new that we'll be able to do with Webb. And I'll be involved in a program that's going to be doing exactly that.
Do we know, do people have a date in mind for first light, that first sort of glimpse through the telescope?
The first few weeks and months after launch are going to be incredibly hectic. So first the observatory will have to deploy and we'll have to travel out to L2. And then gradually we'll start kind of testing all the different functions and operations of all the different systems at the observatory and the science instruments as well. And there's a timeline for that and a process. And that's something that we're actually practicing a lot right now. This is a huge part of the preparations we're currently going through. As soon as a mode or an instrument is kind of what we call ready for science, so we've kind of checked everything and we've verified that everything's working as planned, then we will do some kind of initial observations with that particular instrument or that particular mode. And so that's called the early release observations. And so those will all be released at the end of commissioning. Mm-hmm. Which is, about 6 months after launch.
So this time next year, this is when we should sort of be thinking maybe we'll see some first images. I was wondering as well, so there's been so many instances of space telescopes that have exceeded expectations in terms of lifetime. So Hubble especially just keeps on trucking, right? It's just keeps going. And then Kepler as well had that 5-year extension just due to the cleverness of the engineers at NASA, essentially. So is that possible with James Webb, or is there a hard stop where it physically cannot last any longer than this? Do we have sort of expectations of lifetime, but then if it exceeds, it might go this long? So
the lifetime of Webb is limited by the fuel on board. So Webb's orbit at L2, it's kind of quasi-stable. So we do have to periodically make some adjustments to the orbit to keep it in a stable orbit, basically. And so there's a fuel tank which will be full, but that's basically kind of what ultimately will limit the lifetime. That said, in the kind of whole engineering of the observatory, the design around, the mass and the fuel availability is always done really conservatively. So people kind of really, put in lots and lots of different margins. So now that we have all the hardware and everything's together, we do already know that the mission will be able to last longer than what was originally planned. So the minimum requirement was actually 5 years. And so we already know that we will far be able to exceed that just based on the amount of fuel that we will have on board. What are you going to be doing on launch day? So hiding in a corner. It's quite surreal. It's actually quite surreal that launch day is finally here. It's been a really long road, and and then we have to get to work. That's the thing. The launch is the start. It's been such a long road, but really it's the start. And so we're going to have a really busy 6 months of commissioning. So there's going to be a lot of like round the clock work for all of the different teams and the instruments. So yeah, it's going to be really exciting.
Yeah. Oh, wish I could be in that room with you and all the team though when that happens. Like, give me a fly on the wall.
But yeah, the commission. So we have like a fixed timeline for commissioning, and that starts at like launch minus 15 minutes. So literally, once we're launched, we're like on a schedule.
I love that they're like 15 minutes after launch. So it's like you watch the launch for like 2 minutes till it disappears. You have a little cry, and then the laptop gets cracked. Like, hurry on.
No, exactly. Yeah, exactly. So the telescopes people, like there's a whole, so many different teams, but like the whole telescopes team and the spacecraft team, like they're straight to work, and they'll be working like 12-hour shifts, 24 hours a day,
all in the name of science.
Yeah.
Thank you so much, Sarah, for taking time out of a very, very busy day to chat all things web with me. That was actually a heavily edited version of our chat. We chatted for a lot longer, so I'll post the full version on Sunday, so keep an eye out for that. So I hope this video has got you as excited for the James Webb Space Telescope as I am, as Sarah is, and all my colleagues around the world, and that you'll join us in crossing all of the fingers and all of the toes in hope of a very successful launch this October 2021. Before we get to the bloopers, I just want to say a big thank you to this week's video sponsor, KiwiCo. Now, I get asked all the time by parents for ideas on how to engage their kids of all different ages in science or engineering. And I think the perfect way to do that is with KiwiCo's monthly subscription boxes. They're designed to help kids to become creative problem solvers and critical thinkers, all while having fun too. Each monthly crate is designed by experts and tested by kids, and each one has a different theme. And the different crates are designed for different age ranges. This is one of their 5+ ranges to engage even the youngest kids with concepts in science, maths, and art. Each box comes with all the supplies that you'll need, no need to nip to the shops, plus detailed kid-friendly instructions and a nice little educational magazine so that you can learn more about the box's theme. This box is all about the science of trees and how they take up water. It's a combo of science experiment and a fun balancing game too, which apparently I am terrible at. So if you've got a kid or a big kid like me in your life that you think would enjoy a monthly subscription like this,
head to kiwico.com/Dr Becky 50
and you'll get 50% off your first month of any crate. And note, they ship to 40 countries worldwide. So this is not just for those of you in the US. So check them out. You can click on the link in the description below. So thank you so much to KiwiCo. And now, roll those bloopers. Unlike the Hubble telescope, which could detect mostly visible light, but a little bit of UV and a little bit of infrared. What's infrared? You've still got a huge amount of infrared ration. Apparently infrared's really giving me trouble today. It's literally been designed for this. It can detect incredibly faint things. Infraweb. God, that word is giving me so much trouble today. When it finally launches this October 2021. Does this look really strange? Like, usually people just cross their fingers, but I feel like crossing all the fingers and toes means this strange situation. Oh. James Webb launch, everyone's excited. Bum bum ba dum ba dum bum ba.